Well, yesterday we learned a bit about symbolic manipulation, and we wrote a rather stylized program to implement a pile of calculus rules from a calculus book. Here on the transparencies, we see a bunch of calculus rules from such a book. And of course, what we did is sort of translate these rules into the language of the computer. But of course, that's a sort of funny strategy. Why should we have to translate these rules into the language of the computer? And what do I really mean by that? The program we wrote yesterday was very stylized. It was a conditional, a dispatch on the type of the expression as observed by the rules. And what we see here are rules that say if the object being the derivative is being taken of, if that expression is a constant, then do one thing. If it's a variable, do another thing. If it's a product of a constant times a variable, do something, and so on. There's a sort of a dispatch there on a type. Well, since this has such a stylized behavior and structure, is there some other way of writing this program that's more clear? Well, what's a rule, first of all? What are these rules? Let's think about that. Rules have parts. If you look at these rules in detail, what you see, for example, is the rule has a left-hand side and a right-hand side. Now, each of these rules has a left-hand side and the right-hand side. The left-hand side is somehow compared with the expression you're trying to take the derivative of. The right-hand side is the replacement for that expression. So all rules on this page are something like this. Okay? I have patterns. Okay? And somehow I have to produce, given a pattern, a skeleton. This is a rule. A pattern is something that matches, and a skeleton is something you substitute into in order to get a new expression. So what that means is that the pattern is matched against the expression, which is the source expression, and the result of the application of the rule is to produce a new expression which I'll call a target by instantiation of a skeleton. It's called instantiation. So that is a process by which these rules are described. What I'd like to do today is build a language and a means of interpreting that language, a means of executing that language, where that language allows us to directly express these rules. Okay, and what we're going to do is, instead of bringing the rules to the level of the computer by writing a program that is those rules in the computer's language, at the moment in the Lisp, we're going to bring the computer to the level of us by writing a way by which the computer can understand rules of this sort. This is slightly emphasizing the idea that we had last time, that we're trying to make a solution to a class of problems rather than a particular one. The problem is, if I want to write rules for a different piece of mathematics, say just simple algebraic simplification or something like that, or manipulation of trigonometric functions, I would have to write a different program using yesterday's method. Whereas I would like to encapsulate all of the things that are common to both of those programs, meaning the idea of matching, instantiation, the control structure, which turns out to be very complicated for such a thing. I'd like to encapsulate that separately from the rules themselves. So let's look at, first of all, a representation. I'd like to use the overhead here. There it is. I'd like to look at a representation of the rules of calculus for derivatives in a sort of simple language that I'm writing right here. Now I'm going to avoid worrying about syntax. We can easily pretty this. And I'm not interested in making this. Is indeed ugly. This doesn't look like the beautiful text set dx by dt or something that I'd like to write, but that's not essential. That's sort of an accidental phenomenon. Here we're just worrying about the fact that the structure of the rules is that there is a left-hand side here, represents the thing I want to match against the derivative expression. This is the representation I'm going to say for the derivative of a constant which we will call c with respect to the variable we will call v. And what we will get on the right-hand side is 0. So this represents a rule. The next rule will be the derivative of a variable, which we will call v, with respect to the same variable v, and we get a 1. However, if we have the derivative of a variable called u with respect to a different variable v, we will get 0. I just want you to look at these rules a little bit. Can you see how they fit together? For example, over here, we're going to have the derivative of the sum of an expression called x1 and an expression called x2. These things that begin with question marks are called pattern variables in the language that we're inventing. And you see, we're just making it up. So pattern variables for matching. And so in this, here we have the derivative of the sum of the expression which we will call x1 and the expression we will call x2 with respect to the variable we call v will be, here's the right-hand side, the sum of the derivative of that expression x1 with respect to v. The right-hand side is the skeleton, and the derivative of x2 with respect to v. Colons here will stand for substitution objects. We'll call them their skeleton evaluations. So let me put up here on the blackboard for a second some syntax so we'll know what's going on for this rule language. First of all, we're going to have to worry about for pattern matching. We're going to have things like a symbol like foo matches exactly itself. The expression f of a and b will be used to match any list whose first element is f, whose second element is a, and whose third element is b. Also, another thing we might have in a pattern is that a question mark with some variable like x. And what that means, it says matches anything which we will call x. Question mark cx will match only constants. So this is something which matches a constant. Call it x. And question mark vx will match a variable. Which we call x. So this is sort of the language we're making up now. If I match two things against each other, then they are compared element by element. But elements in the pattern may contain these syntactic variables, pattern variables, which will be used to match arbitrary objects. And we'll get that object as the value in the name x here, for example. Now, when we make skeletons for instantiation, well, then we have things like this. Foo, a symbol, instantiates to itself. Something which is a list, like f of a and b, instantiates to what f instantiates to a three list, a list of three elements, okay, which are the results of instantiating each of f, a, and b. Okay? And x will be instantiate to the value of x as in the matched pattern. So going back to the overhead here, we see that all of those kinds of objects. We see here a pattern variable which matches a constant, a pattern variable which matches a variable, a pattern variable which will match anything. And if we have two instances of the same name, like this is the derivative of the expression which is a variable only, whose name will be v, with respect to some arbitrary expression which we will call v, since this v appears twice, we're going to want that to mean they have to be the same. The only consistent match is that those are the same. So here we're making up a language. And in fact, that's a very nice thing to be doing. It's so much fun to make up a language. And you do this all the time, and the really most powerful design things you ever do are sort of making up a language to solve problems like this. Now, here we go back here and look at some of these rules. Well, there's a whole set of them. I mean, there's one for addition and one for multiplication, just like we had before. The derivative of the product of x1 and x2 with respect to v is the sum of the product of x1 and the derivative of x2 with respect to v, and the product of the derivative of x1 and x2. And here we have exponentiation, and of course we run off the end down here. We can add as many as we like. But the whole thing over here, I'm giving this list of rules the name derivative rules. What would we do with such a thing once we have it? Well, one of the nicest ideas, first of all, is I'm going to write for you, and we're going to play with it all day. What I'm going to write for you is a program called Simplifier, the general purpose simplifier. I'm going to say something like define dsimp to be a simplifier of the derivative rules. And what simplifier is going to do is, given a set of rules, it will produce for me a procedure which will simplify expressions containing the things that are referred to by these rules. So here will be a procedure constructed for your purposes to simplify things with derivatives in them, such that after that, if we're typing at some list system and we get a prompt and we say dsimp, for example, of the derivative of the sum of x and y with respect to x. Note the quote here because I'm talking about the expression, which is the derivative. Okay. Then I will get back, as a result, plus 1, 0. because the derivative of x plus y is derivative of x plus derivative of y. Derivative of x with respect to x is 1. Derivative of y with respect to x is 0. So that's what we're going to get. I haven't put a simplification at that level, algebraic simplification yet. Of course, once we have such a thing, then we can look at other rules. So, for example, we can, if we go to the slide, okay, here, for example, are other rules that we might have, algebraic manipulation rules, ones that would be used for simplifying algebraic expressions. For example, just looking at some of these, the left-hand side says any operator applied to a constant E1 and a constant E2 is the result of evaluating that operator on the constants, E1 and E2. Or an operator applied to E1, any expression E1 and a constant E2 is going to move the constant forward. So that'll turn into the operator with E2 followed by E1. Okay, why I did that, I don't know. It wouldn't work if I had division, okay, for example. So that's a bug in the rules, if you like. Okay? So the sum of 0 and E is E. The product of 1 and any expression E is E. The product of 0 and any expression E is 0. Just looking at some more of these rules, we can have arbitrarily complicated ones. We can have things like the product of the constant E1 and any constant E2 with E3 is the result of multiplying now the constants E1 and E2 together and putting E3 there. So it says combine the constants that I had, which was if I had a product of E1 and E2 and E3, just multiply, and E1 and E2 are both constants, multiply them. Okay? And you can make up the rules as you like. There are lots of them here. Okay, there are things as complicated, for example, as, I suppose down here some distributive law, you see. The product of any object C and the sum of D and E is the same as the sum of the product of C and D and the product of C and E. Okay? Now, what exactly these rules are doesn't very much interest me. We're going to writing a language so that would allow us to interpret these rules, so that we can, in fact, make up whatever rules we like. Another whole language of programming. Well, let's see. I haven't told you how we're going to do this. And, of course, for a while we're going to work on that. But there's a real question of what am I going to do at all at a large scale? Okay? How do these rules work? How is the simplifier program going to manipulate these rules with your expression to produce a reasonable answer? Well, first I'd like to think about these rules as being some sort of deck of them. Okay? So here we have a whole bunch of rules. Right? Each rule, here's a rule, has a pattern and a skeleton. I'm trying to make up a control structure for this. Now, what I have is a matcher, and I have something which is an instantiator. And I'm going to pass from the matcher to the instantiator a set of meanings for the pattern variables. A dictionary, I'll call it. A dictionary. Which will say X was matched against the following subexpression. And Y was matched against another following subexpression. And from the instantiator, I will be making expressions, and they will go into the matcher. There will be expressions. And the patterns of the rules will be fed into the matcher, and the skeletons from the same rule will be fed into the instantiator. Now, this is a little complicated, because when you have something like an algebraic expression, where the rules are intended to allow you to substitute equals for equals. These are equal transformation rules. So all subexpressions of the expression should be looked at. You give it an expression, this thing, and the rules should be cycled around, first of all, for every subexpression of the expression you feed in. all of the rules must be tried and looked at. And if any rule matches, then this process occurs. The dictionary has some values in it. The instantiator makes a new expression, which is basically replaces that part of the expression that was matched in your original expression. And then of course, we're going to recheck that. Going to go around these rules again, seeing if that can be simplified further. And then we're going to do that for every sub-expression until the thing no longer changes. You can think of this as sort of an organic process. You've got some sort of stew, right? You've got bacteria or something, or enzymes in some gooey mess. And there's you stick it, and these enzymes change things. They attach to your expression, change it, and then they go away. Okay, they have to match. It's a key and lock phenomenon. They match, they change it, they go away. You can imagine it's a parallel process of some sort. Okay? So you stick an expression into this mess, and after a while you take it out and it's been simplified. Okay? And it just keeps changing until it no longer can be changed. But these enzymes can attach to any part of the expression. Okay. At this point, I'd like to stop and ask questions. Yes?
This implies that the matching program and the instantiation program are separate programs. Is that right, or is that they are?
They're separate little pieces. They fit together in a larger structure.
So I'm going through and matching and passing the information about what I matched to an instantiator, which makes the changes, and then I pass that back into
It won't
the
make a change. It will make a new expression which has substituted the values of the pattern variables that were matched on the left-hand side for the variables that are mentioned, the skeleton variables or evaluation variables, whatever I forgot what I call them, on the right-hand side. Okay?
And then that's passed back into the matcher.
Then this is going to go around again. This is going to go through this mess until it no longer changes.
And it seems that there would be a danger of getting into a recursive loop.
Yes. Yes, if you don't write your rules nicely. Indeed, in any programming language you invent, if it's sufficiently powerful to do anything, you can write programs that will go into infinite loops. And indeed, writing a program for doing algebraic manipulation wrong will produce infinite loops. Go ahead.
Some language designers feel that this feature is so important that it should become part of the basic language, for example, scheme in this case. What are your thoughts on
which
this,
language feature?
The pattern matching and all application of such rules should be
you mean like
just
Prolog,
like Emacs,
like Prolog,
like Prolog, but
well,
become a more general.
It's possible. Okay, I think my feeling about that is that I would like to teach you how to do it so you don't depend upon some language designer.
Okay.
You make it yourself. You can roll your own. Thank you.